Hello everyone. This is LumaSleep, an active IoT-based system for sleep monitoring and environmental control. This project is by myself, Amr Jallad, along with Muhammad Samer and Musa Hirzallah, supervised by Dr. Maryam Bittayeb at Abu Dhabi University. In this video, we will go through the problem we are solving, our key contributions, and the full system architecture. So let's get started. So here's the issue. Today's sleep trackers like Fitbit or Apple Watch are all passive. They tell you after you wake up that you slept badly. They give you your charts and sleep score, but they don't actually do anything while you're sleeping. You still have to read the data yourself and adjust your room yourself. And realistically, most people just don't bother. So nobody follows through and sleep stays poor. LumaSleep flips this around. Instead of just watching you sleep, it monitors your body signals in real time and automatically adjusts your room, including lights, temperature, curtains, and sound, without waking you up. We have three main contributions. First is Edge AI privacy. All processing happens locally on our Raspberry Pi 5. Your health data never leaves your home and nothing goes to the cloud. Second, closed loop automation. We connect wearable sensing directly to smart home control. The system detects your sleep stage and responds right away. Third, home ready design. You don't need expensive lab equipment or any extra things. The system works with normal off-the-shelf smart home devices that are already available in the market. So here's our how our project works and how is like the system works. Your smartwatch streams heart rate and the motion data over MQTT and Wi-Fi to the gateway, which is our Raspberry Pi. The gateway cleans the data by removing noise and filling in the gaps, then breaks it into 30 seconds windows. Each window goes into an LSTM neural network that classifies your current sleep stage. This all happens locally on the device, which keeps the delay very low. The prediction then go to rule-based decision layer. For example, if the system detects deep sleep, it dims the lights, lowers the temperature, and manages background sleep. These commands go out over Zigbee, which is a separate lower power network, so it doesn't slow down your home Wi-Fi. And at the same time, an encrypted connection sends a summary to mobile dashboard, so you can review your sleep quality, heart rate trends, and everything the system did overnight.
Thank you. Now for the system results and simulation, we created a system running live on a real 30-second sensor window. Starting on the top left of the results, the pipeline actually catches a dropped Bluetooth packet at second 14 and recovers it through linear interpolation. Then a Butterworth low-pass filter smooths out the noise so that the LSTM model actually sees the clean trend rather than just raw variability. Now for the two features, such as the heart rate and motion, which are the two main features. They are normalized using min-max scaling to a 0 to 1 scale and fed into the model, which then outputs an 82% confidence rate for deep sleep, clearing our 75% threshold. Actually, it is exceeding it. So rather than acting on a one window alone, a majority vote across the last 5 windows instead confirms deep sleep, and the final summary on the bottom right shows that the Zigbee command was dispatched, every gate cleared end to end. Now for the environmental decision rules, once a stage is confirmed, the system knows exactly how to respond. Now for light sleep gets a 10% warm dim and partially closed curtains, subtle and non-disruptive at all. Now for deep sleep, it cuts the light entirely and drops the HVAC to 19 degrees Celsius, which is the AC. Now since cooler temperatures actively support restorative sleep, this is why it drops the HVAC to the temperature that it is. Now for the REM, it keeps lights off but raises the temperature slightly by 0.5 degrees Celsius because the body's temperature regulation is suppressed during REM and a small warming helps sustain it. These aren't arbitrary settings, they're grounded in sleep science. Now for the system in action, this is a full loop running in real time. Now the wearable detects a shift to deep sleep and streams the data to the gateway immediately, which pre-processes and run inferences on device. No cloud needed at all for security reasons. Now the decision layer clears the confidence check as well, the majority vote and the hysteresis lockout. Then fires the Zigbee command immediately. Now also for the room to physically respond, it will turn off the light. It will turn the HVAC system to 19 degrees Celsius as well. 30 seconds later, it re-evaluates. If the stage holds, nothing changes at all. If it shifts, the environment adapts. The system is always watching but never overreacting. So it operates on a 530-second windows. Now, for the AI inference, the classifier is a pre-trained LSTM. The reason why we chose it is specifically because sleep staging is a time series problem. What stage you're in depends on what happens 10 minutes ago. An LSTM has a temporal memory built in. Modern models do not have that at all and only look at the specific time window that it currently analyzes. So it's not good at all. Now it runs two hidden layers of 64 units, which with the 0.2 dropout. It takes our 30-second normalized HR and motion windows as input and outputs the four stage probabilities basically that we saw in the pipeline report together. Now, lightweight enough. It is also lightweight enough, to run fully on an edge gateway.
To evaluate LumaSleep, we focus on four main performance areas. First, the AI model should achieve an overall classification accuracy and F1 score above 85% across the four sleep stages. This is important because the system must correctly identify the user's sleep stage before making any environmental adjustment. Second, the system latency should be less than 200 milliseconds from the sensor reading to the actuator response. This allows the system to react in real time without a noticeable delay. Third, the network reliability target is more than 99% packet delivery using MQTT and Zigbee during overnight testing. Since the system operates while the user is sleeping, stable communication is essential. Finally, for future sleep impact, the goal is to improve sleep efficiency by around 10% compared with the passive trackers. So LumaSleep is designed not only to monitor sleep, but to also actively improve it. Now for our validation roadmap, it is divided into three main phases. Phase 1 focuses on hardware integration. This includes connecting the wearable sensors, the Raspberry Pi gateway, and the pre-trained LSTM model so the system can receive and process sleep data locally. Phase 2 focuses on technical benchmarking. At this stage, latency, network reliability, and overnight soak testing are measured to ensure that the system can operate continuously and reliably. Phase 3 moves towards human trials. This would involve A/B testing, where sleep with passive tracking is compared to sleep with active environmental control. The aim is to measure whether LumaSleep can improve sleep efficiency in real use. Overall, the roadmap begins with building the technical foundation, then testing system performance, and finally validating the sleep improvement impact. To conclude, LumaSleep is currently a conceptual architecture, and the physical prototype deployment is planned as a future step. One limitation is that autonomous operation depends heavily on stable local Wi-Fi and Zigbee. If the network becomes unstable, the system response may be affected. However, the main value of LumaSleep is that it shifts sleep technology from a passive observation to an active intervention. Instead of only giving the user a summary after waking up, it monitors sleep in real time and adjusts the environment dynamically. Another key advantage is edge privacy. Since the pre-trained LSTM model runs locally on the Raspberry Pi, sensitive psychological data does not need to be sent to the cloud. In summary, LumaSleep provides a privacy-aware, IoT-based, and AI-driven approach to sleep monitoring, with the goal of improving sleep quality through real-time environmental control. Thank you for listening, and I hope you like this idea.